In this video, we're going to take a look at both inter and intramolecular forces and identify how those can help us explain some of the properties of certain molecules. And then we're going to transition into talking about metallic bonding. We haven't done that yet, so we'll throw that into this lesson as well. So the first force is intramolecular force. So whenever you have the prefix intra, that means that it's within. So those are the forces within molecules. So there are forces of electrostatic attraction within a molecule. And they occur between the nuclei of atoms. So remember, the nuclei of an atom is positive because of the protons that are within it. And then the electrons that make up the molecule. So these would be covalent bonds, metallic bonds, and ionic bonds. These types of forces have to be broken by chemical means. So they're very strong forces. They hold the molecule together, and the only way they can be broken is through a chemical reaction where you would produce new products. Intermolecular forces, on the other hand, are forces of attraction between two molecules. So they're much weaker than the intramolecular forces, or our bonds, and they're much easier to break. Now, there are different degrees of intermolecular forces, which we'll talk about. So the things that cause changes with intermolecular forces, so physical changes will break or weaken these forces. So as you heat up a substance, these forces will become reduced, and then they'll break apart. So these molecules won't be attracted to one another as much. These forces affect the melting and boiling points of substances. And we'll look at the three different forces. So one of them is called van der Waals forces, or London forces. The other one is called dipole-dipole interactions. And the last one is called hydrogen bonding, which is a special form of dipole-dipole interaction. So the first type of interaction is known as London dispersion forces. So this is when the electrons from one molecule get attracted to the positive nucleus of the neighboring molecule. So if imagine this was a molecule, these are actually helium atoms, but this electron is being attracted to the nucleus, this one's being attracted to this nucleus, and so on. So there are attractive forces. But then at the same time, there are also some repulsive forces. So the electrons themselves will push against each other, and the protons themselves will push against each other. So this force is much more weak than some of the other ones that we're going to learn about. So the greater the number of electrons and protons, the greater the force of attraction. So the bigger the molecules and the atoms, the more attraction there will be. This is the only force that's used to hold nonpolar molecules together, because the other two only have to do with polar molecules. So things that would have London dispersion forces would be nonpolar things like methane, ethane, so hydrocarbons, and like carbon dioxide is nonpolar. So those sorts of molecules would be held together only by London dispersion forces. These are also called van der Waals forces as well. So the next type of force are called dipole-dipole interactions. So they're stronger than London forces. So I forgot to mention, London forces are involved in all molecules. So even if they're polar, there will be London dispersion forces at play. So if they're polar, they then have London forces of attraction, but also dipole-dipole interactions. These forces of attraction will be stronger because there's actually two forces at play holding molecules close together. So dipole-dipole interactions occur between polar molecules that have dipoles. So what happens is the negative dipole of one will be attracted to the positive dipole of another. So this image from our cognitive textbook demonstrates that. So the chloride ion is attracted to the positive dipole of another neighboring molecule, the hydrogen ion. So the strength of the force is related to the polarity of the given molecule. So the more polar it is, the stronger the force of attraction. Our third type of interaction is hydrogen bonds. So this is a specific type of dipole-dipole interaction, and it occurs between hydrogen atoms in one, or hydrogen ions in one molecule, and then highly electronegative atoms in the other neighboring. So fluorine, oxygen, nitrogen, sulfur, and phosphorus have high electronegativities, so the force of attraction will be greater. They also often have unshared pairs of electrons present. So if you look at water, that's a prime example. So oxygen is not only highly electronegative, it also has 2 lone pairs of electrons here. So this is a very strong force of attraction. And this is the strongest of the intermolecular forces, and it will affect melting and boiling points significantly. So we'll look at some of those interactions in the next few moments. We usually demonstrate the intramolecular bonds with a solid line, and then the hydrogen bonds or dipole interactions we represent with a dotted or a hashed line like this. So because more polar molecules have stronger dipole-dipole interactions or hydrogen bonding, they will have higher melting and boiling points. And that's because the molecules are being held more tightly together. So it's harder to break those forces of attraction. So it will take more energy to separate them to allow for a change in state from solid to liquid and then from liquid to gas. So the greater the number of electrons per molecule, the stronger the London forces as well. So that will also affect the melting and boiling point. So larger molecules have more electrons, so that means that they will have a higher molar mass, etc., and the London forces will be stronger. So that would be a reason why they would be have larger molecules have higher melting and boiling points. And then substances with hydrogen bonding will have the highest melting and boiling points because their force of attraction is very strong. So this graph from our Cognitivity textbook is really well explained in section 4.4.1, but I'll explain it a little bit here. So this shows you the effect of hydrogen bonding on boiling point. So it traces the group 14, group 15, 16, 17, certain compounds, so across period 3, or across the periods and so on. So this is group 14, so we have carbon, then silicon, then germanium, and then tin. These molecules are nonpolar, so that means that they have a lower melting and boiling point. So that's why their properties are at the bottom. But as you go across, the molar mass is getting bigger and bigger, so the melting and boiling point is increasing. So there's increased London forces as you go, so that impacts the melting and boiling point. Then these next 3, they all follow a general trend. These are the most electronegative, so these ones are exhibiting hydrogen bonding. So these all have high boiling points. Water is extremely polar, so this is why it has the highest, because it has very strong hydrogen bond forces. Hydrogen fluoride also. But then when you go down here, these are much less electronegative in terms of the differences. So there's a drop. But then as they get bigger and bigger, as you move down the group, there's going to be a general increase again. So this shows you the trend, and it shows you that hydrogen bonding has a huge impact on boiling point, even amongst a group. So if there wasn't that hydrogen bonding, all of the graphs or all of the lines would follow the trend of the first one. But because of the hydrogen bonding, there's really high melting point, then there's a big drop as you go to something that's not involved with hydrogen bonding, and then slow increase as you move down the group. So hydrogen bonding is responsible for ice's reduced density. So what happens is, as water is converting it from a liquid to a solid, the hydrogen bonds will hold the water molecules in a rigid open structure, which gives it a lower density than liquid water. So this open structure allows ice to float. When we get to our solutions and solubility unit, we'll spend more time talking about solubility. But water is called the universal solvent, which means that ionic compounds dissolve in water because it's polar, so they dissociate into ions. Now, ionic compounds, not all will dissolve. There will be different degrees of solubility, but as a general rule, ionic compounds can dissolve in water. Then polar molecules can also dissolve because of the hydrogen bonding that they exhibit with water. So the more polar they are, the more soluble they'll be. So we have talked about ionic bonding and covalent bonding, but we skipped over metallic bonding. So there's a few properties that we should recognize in terms of metallic bonding. We don't spend much time talking about metals alone, but they can form alloys, which we'll discuss in this brief little review. So in grade 9 and grade 10 and even now, we've discussed the properties of metal. So metals are shiny. They're not always shiny at the outstart. Sometimes you have to polish them to make them shiny again. They're ductile, which means that you can pull metals into wires. They're also malleable, so you can hammer them and they'll flatten out. And then finally, they're really good conductors of heat and electricity. So metals are actually really special, and it's their bonding that gives them their unique properties. So metals will form lattices of positive ions, and their valence electrons will delocalize and they'll move freely through the structure. So you end up with these positive metal ions, and their valence electrons just kind of float freely throughout the structure, which gives metals some of their unique properties that we'll discuss. So the metallic bond itself is the electrostatic attraction between the positive metal ions and the delocalized electrons. And if you put stress on the surface, the metal ions they're not harmed. They actually just slide across each other, but the bond isn't impacted. So this shows you what happens. So some stress is put here and stress is put here, and that just pushes these that way and these that way. So this explains metals' malleability and ductility. It's why they're not considered brittle. If voltage is applied to a metal, the delocalized electrons will be repelled towards the positive electrode, and that will explain metals' electrical conductivity. So the electrons just travel right through the metal towards the positive electrode. So that's why metals are good electrical conductors. Those delocalized electrons can also carry heat very well. So they can transfer the heat from a hotter region, so wherever the heat source is, throughout to the cooler regions of the metal, spreading that heat throughout. So that's why metals are really good conductors of heat as well. We often say that metals are shiny, like we said, once they're polished. So that has to do with their luster. So the delocalized electrons actually give metals their shininess, and that's because they reflect wavelengths of light, giving that reflection of light back to your eye, which makes them look shiny. Now, the bond strength of different metals depends on two things. So it depends on the charge of the metal ion and then the ionic radius. So the stronger the bond, the higher the melting point. So if we look at two similar ions, potassium and calcium, which are next door to one another, potassium has an ionic charge of +1, and its radius is 138 times 10 to the negative 12 meters, and its melting point is 63.4 degrees Celsius. So it melts at a very low temperature. Calcium, which is right next door, it has an ionic charge of 2+. Its ionic radius is smaller, so it's 100 times 10 to the negative 12 meters. But its melting point is 840 degrees Celsius. So the ionic charge and that radius impacts the melting point. So this would be a stronger bond. So it's less, it would be less malleable too. And if you've ever, potassium you can slice with a knife, but calcium would be harder to do so. So metals can also form alloys with one another and other substances. So an alloy is a homogeneous or homogeneous mixture of two or more metals, or even metals with some nonmetals. So they're often stronger than their individual metal components. So, for example, if you add carbon to iron, it will make it much stronger. So a pure metal, when you apply force to it, remember the ions will slide across one another, so layers can slide over one another. But once you add in other components, if this was steel, for instance, and we added in some carbon, when you apply the force, the layers can't slide over each other anymore. So this actually makes them stronger. And this table from our cognitive textbook shows some properties of some selected alloys. You don't need to memorize them, but I just thought it was interesting to take a look at. So brass is a mixture of 70% copper and 30% zinc. So it's harder than pure copper, and we use brass to make musical instruments and other things, but that's one use for them. Bronze is 90% copper and 10% tin. It's harder than pure copper, and it's often used to make statues. It also doesn't get that green patina that you would see on pure copper. So mild steel is 99.7% iron and 0.3% carbon. So that would be stronger and harder than pure iron. Stainless steel, you would find that in kitchen appliances and maybe your kitchen sink, or even your cutlery. So that's 74% iron, 18% chromium, and 8% nickel. So it is resistant to corrosion. That's where the stainless comes from. And then it's used to make cutlery. It might be used to make your kitchen sink and so on. And then solder is used to lower the melting points of metals to be able to fuse two things together. So lead solder is 50% tin and 50% lead. We tend not to use that as much because lead being, a neurotoxin, a heavy metal. Lead-free solder is a mixture of tin with a variety of other metals like copper, silver, bismuth, indium, zinc, or antimony. And solder is used because they have lower melting points than tin or lead, so we can use those in electrical circuit boards, or again, when you're trying to fuse two metals together, the solder can act as the bridge and hold those two things together. So if you've ever soldered something, you might have used some solder before.